So you might recollect that we have divided this whole course into 4 quadrants where we looked at kinetics, kinematics, rigid body and particles, right? So pretty much done with 3 quadrants here. Now we are getting into rigid body dynamics where we're getting into the kinetics of it. So it's essentially the 4th quadrant of that. And it's not like a separate body of knowledge. Whatever we learned from those 3 other quadrants, we are going to use that as the foundation to build upon the kinetics for the rigid body. Okay, so kinetics, as you might recollect, is essentially talking about the cause of the motion as well, which means that we will bring in both the forces and the moments. Unlike for the particle where only the force was sufficient, here it's not only the force which is a cause, but moments could be a cause as well, because rigid body dynamics in general involves rotation. But we will take baby steps towards it once again, and so we will start with just translation alone, because we are familiar with that from the whatever we have looked at from the kinetics of the particle. Because remember that whenever we've been talking about kinematics, but we've been quite frequently invoking Newton's second law, the force is equal to mass into acceleration, and that's essentially kinetics. So we've already been using that, and you've been using forces both as inputs as well as outputs for some of your homework so far as well. So you're already familiar with the kinetics of particles. It's not nothing much over there. So that's why the kinetics of rigid body dynamics would also be fairly easy to look at once you understand the kinetics of particles, which you do. Okay, so now as I said, before we venture into rotations and moments, we will look at translations. And the rigid body, just like any other body, is essentially made out of an infinite number of particles. But the fact that it is rigid means that you don't need to consider each one of them individually, unlike in a flexible structure, a deformable body. In structural analysis, for example, it would in reality be an infinite degree of freedom system, but then there are ways to bring it down to a finite number of degrees of freedom as an approximation. Whereas here you don't really need an approximation. The fact that it is rigid, which means that it's not at all flexible, means that it will be just a 6 degree of freedom system. In other words, it will have 3 translations and 3 rotations. Now, where do you put that translation to is up to you as an analyst. You have the freedom to assign those translations to any particular point of the rigid body. It could actually be a material point. It need not be a material point, like a hollow sphere center need not be a material point, or it could be somewhere outside the entire body as well. But more often than not, it's very convenient to choose that point as the so-called center of mass. Okay, so center of mass is something you are also familiar with the center of gravity. Can anybody say what's the difference between a center of mass and a center of gravity? Is there a difference at all, or they're just synonymous?
I feel like my understanding is that they're the same thing. It's more about like what they mean. Like the center of gravity is the point where if we change gravity from a distributed force to a concentrated force, it acts like the center of mass, but that is the same location. Or it acts at the center of gravity, but that's the same location as the center of mass.
Okay, heading in the right direction, but can you first of all distinguish mass and weight? Then you will be able to get to what we are trying to look at.
So mass is the stuff that makes up an object, and the weight is the force of gravity on that mass.
Mm-hmm. Okay, so in terms of an equation, what is the factor which distinguishes an m and a w, a mass and a weight?
It's the acceleration due to gravity.
Right, so that's small g, right? Now, if you have that small g constant throughout the body, then you would have both of these identical. So center of mass as well as center of gravity, Cm and Cg is what the abbreviations that we will use, will be identical only if g is a constant throughout that particular body, and which is true for most of the flying vehicles that we make, right? As human beings, whatever we fly, whether it's on Earth or in space, we typically have a situation where it's reasonably small compared to the planetary bodies, for example, and therefore it's okay. But sometimes you have very long booms for your antenna, etc., and the satellite may be very close or equal in terms of orders of magnitude, somewhat equidistant from two planetary bodies. In such a situation, you could have a field difference in small g, and therefore your CG and CM could in general be different from each other. So you just need to be a little bit aware of that. Okay. Whereas for most of what we will be doing here, the center of mass is what we will be looking at. Now those are 2 points, center of mass and center of gravity. I assume you would have also heard of this term centroid. Are you familiar with that? What's the difference between centroid and center of mass? Are they the same?
Centroid is the geometric center, and I think they are the same if the object has a constant density.
Excellent, yeah. So essentially, as he said, it's purely geometric property, the centroid, where the weightage that you're taking is in terms of the areas or the volumes, depending upon whether it's a 2D problem or a 3D problem that you're looking at. Whereas the weightage in the case of the center of mass calculations is the mass. So that is what is going to be the weightage that you're going to take in deriving that. And similarly, when you're looking at center of gravity, you'd be looking at the weight. So the weight is the weight is the weighting factor over there. The weight, which is mass times gravity as acceleration due to gravity, as Daniel just pointed out. Okay, so just be aware of these things. Sometimes beginners tend to confuse between these three and tend to interchangeably use them. It's okay in terms of a language when you do that, but when it gets into the equation, sometimes it could cause issues. Okay. Now, in each one of these slides, or most of the slides that I'll be presenting today, we'll have a title, and we'll also have the end result that I will already put up over here, and then we will walk through the steps in order to arrive at that. Okay. Now, this is something that we've been talking right from class 1, and which you are aware of even from school, which is Sir Isaac Newton's laws of motion, right? The first law, second law, and third law. And the first law can always be thought of as a special case of the second law, because the second law, what it says is that in the most general form, it says that whatever is the resultant force that is applied on a body or a set of particles for that matter is essentially the rate of change of what we call as the translational momentum. Okay, the translational momentum defined as the mass times the velocity. And in situations where the mass doesn't vary, then you can take the mass out, and time rate of change of the velocity in an inertial frame of reference becomes acceleration. That's the ma that you have. But pretty much all the flying vehicles that we deal with, be it an aircraft, helicopter, satellite, launch vehicle, missile, whatever you consider, all of them will have a change in m because you're burning fuel, right? Which means that an aircraft which takes off is typically heavier compared to the aircraft which lands quite a bit, okay? Because the fuel weight fractions are fairly large, especially when you're looking at, let's say, intercontinental flights or intercontinental ballistic missiles, etc. And in rockets, it's even more, because it's not just the fuel that you're carrying the oxidizer as well as a propellant, right? Which means that the reduction in weight is far more from the propellant point of view, and also because it's typically multi-stage, and you're jettisoning the stages once their propellant is finished, right? So there is a continuous decrease because of the propellant burn. There is also a discrete drop in the weight because of the jettisoning of the earlier stages which have already been finished in terms of the propellant, right? So those things will cause your m dot to have a continuous value and also a piecewise continuous value, and you have to account for that. But in this course, for most parts, we will be looking at m constant, or in other words, treating 2 points where the m doesn't change so much. So the more important change would be the change in v that we would be looking at, and therefore this would be an appropriate thing. So remember that this right end is the approximation, whereas this is a much more accurate way of putting it, and which will take into account changes in the mass as well. So one is to introduce the concept of acceleration, which is of course the translational acceleration, because now we are aware of things both in the rotational and the translational sense. A lot of people would call it linear acceleration. I would, as I said before, want you to avoid that, because there's a conflict between linear and non-linear kind of a difference over there. So I would rather call it translational and rotational acceleration. What we have here is the translational. Okay, we had to get into the rotational, which of course we introduced earlier, omega and alpha, and you used it for some problems as well. Omega would be the angular velocity and alpha would be the angular acceleration. And these are typically standard notations that I used, and therefore I would urge you to avoid using those omega, alpha, a, v, etc. for some other variables, because it can cause confusion in the overall dynamics derivations. Okay. Now, also it's understood whenever we don't put prefix superscript that this is in the inertial frame of reference, and we have already said that these laws are valid only in inertial frames of reference, and hence this itself is already an approximation, okay, because we, as I said, we don't have any truly inertial frames of reference, because true inertial frame of reference should neither be accelerating nor should it be rotating, and you don't find any such body on this universe, in this universe, and therefore you cannot really have an exact equal to sign, but for all practical purposes it is valid. This is a further approximation that you're taking, that the mass is not changing as well, and therefore you're getting to that. And the source of this equation, the form that is presented here, of course, dates back quite a bit, more than 350 years. So the Principia, which Newton wrote in 1687. So he pretty much lived in the 17th century, and that's exactly what led to this, amongst many other things. Okay. So once again, you're familiar with these assumptions. We visited this in an earlier class, but just to put them all together, in order to arrive at this, he assumed an inertial frame of reference, which is now, of course, named after him. We call it a Newtonian frame of reference, but later people realized that Galileo had worked on this much earlier to Newton, and to honor him as well, sometimes it is interchangeably called as a Galilean frame of reference. So it doesn't matter whether you call it inertial, Newtonian or Galilean. Essentially it means that frame is neither accelerating nor rotating. These are the two important points from a physics or a mathematics point of view that you need to remember. The second, so that is the approximation required for the first equal to sign on this in this equation. The second equal to sign also requires your constant mass, and this is of course only for versions where you're not dealing with translational momentum, rather you're dealing with acceleration, because you're more comfortable with that idea, and therefore you will have to live with that additional approximation. So even for transport vehicles, if you're taking a very short thing, let's say an aircraft is maneuvering, so from the start of the maneuver to the end of the maneuver, there will be a fuel consumption, but it will not be as much as it is from takeoff to landing, and therefore the change m dot that you're going to have may not be significantly causing changes to this equation, and therefore this might be a reasonable approximation. Okay, but both these you ought to remember very clearly are approximations. Okay, and but we use them day in and day out, and for and with great results as well, which means that the approximation is a reasonably good approximation. The third thing, which is where the lacuna comes in, and therefore the rest of the dynamics course that we are going to deal with, is the fact that this is valid only for particles. Yes, Newton applied it to planets, and planets are not particles, they are huge stuff, but essentially he shrunk them to the center of mass, and therefore he was able to deal with that when he says the law of gravitation, the force is equal to Gmm by r squared, where capital G, uppercase G, is the universal gravitational constant, not the acceleration due to gravity, is essentially an approximation that we are trying to do, where we are treating a finite sized body, in fact massive body, into considering it as zero sized or a particle. Okay, and So which is what is written in the bracket over there. It is valid for particle bodies as well, as long as you're idealizing it as particle, which means that you're assuming all of that mass is concentrated at a point, and typically that point is chosen as the center of mass so that you don't have additional complications in the equation. But that's not necessary. You could assign it to some other point, and then you would have something else in order to take care of the mathematics, what is missing by pushing it to a point other than the center of mass. But let's keep that aside. But it's important to remember that not only Galileo and Newton, but even Kepler, who came up with the laws of planetary motion, all of them, for most of their derivations, treated these massive bodies as particles. Okay, but in reality, that's not valid as well. So we have those three different. Just need a signature. You have a pen, not you? Anything else?
That's all.
That's it. Welcome. How's your health?
Yeah, it's fine. It's very good.
Okay, so these are the three assumptions that we should be aware of, and the errors coming out of it could be different depending upon which bodies you're considering, what kind of motions you're considering, etc. So just keep this at the back of your mind, because you might have to relax either one or of two or all three of these assumptions at certain points. Okay, the first one, if you relax, then pretty much you don't have much to work with except experiments and things like that. But the other two, at least sometimes you might have to give up in order to get more accurate results. Okay, so the Newton's second law of motion, as I said, of which the first law is a special case. Can you argue it out why the Newton's first law can be thought of as a special case of the second law, just by looking at this part of the equation? You remember the statement of Newton's first law, right? A body which is in uniform motion continues to be in uniform motion unless and until it's acted upon by a force. So in other words, it doesn't change its direction, nor does it change its magnitude of the velocity. So speed and the direction remain the same. So we want to see what is the situation there. Can we apply Newton's second law over there and realize or recognize that that is just a special case of the second law?
Is it that if you have a non-zero force, that would indicate that there is a change, like a change shouldn't exist, so there's a change in the mass or velocity?
Absolutely, absolutely. And the corollary of that, because he says unless and until acted upon by a force, which means that force is equal to zero, right? So if the force is equal to zero, what happens? The d by dt in an inertial frame of this quantity becomes zero. Okay, so what does d by dt of something being zero mean?
There wasn't any change in the mass or the
Exactly, exactly. So essentially what is inside the bracket is a constant, right? And if you're assuming also that the mass is a constant like you did, essentially means your velocity is a constant. And if velocity is a constant, which is a vector, it means both the magnitude and the direction are constant, okay? They don't change. So it's essentially what the first law is saying, okay? So since the first law is a fallout of the second law, it's essentially a simpler case than what the second law considers. Second law considers non-zero forces, whereas the first law considers zero forces, and therefore is able to make some conclusion about V, assuming also that M is equal to a constant. Okay, so you see that both of these are therefore dependent on this particular assumption of inertial frame of reference, or the Newtonian or Galilean frame of reference, which does not exist, and therefore this is always to question when you want it in a more scientific manner. You want to have things very rigorous, but for all engineering purposes, this is a very good approximation, and that's what we've been using to make so many different vehicles, as we know, right? So that's as far as the first and second law are concerned. Both are dependent on an erroneous assumption of inertial frame of reference. But the third law, very interestingly, is a universal law. That is the third law, which says nothing but the principle of reciprocity. So in other words, every action has an equal and opposite reaction. That's something which is valid not only in continuum mechanics, that is your classical mechanics, or also known as Newtonian mechanics, but even if you go to, let's say, relativity, Einstein's kind of special theory or the general theory, or you go to quantum mechanics, where you're essentially dealing with things which are very, very small. So in other words, the principle of reciprocity is what in the Indian culture is called as the law of karmā. So essentially every action that either a body or a human being or any living being or non-living thing does is essentially going to have certain repercussions. Okay, so those repercussions cannot be escaped however fast you try to escape from it, which is what it means that this is still valid in the theory of relativity as well. And at the same time, however small you become, which is essentially what you're looking at, disappearing. So whether you disappear or escape very fast, you have no escape from the law of karma, which is true whether it's a living being or a non-living entity. And that's one of the few laws which are so universal in nature, which is across the classical physics, which is continuum mechanics, and also it applies equally well to relativistic mechanics and the quantum mechanics as well. Okay, so just keep that in mind, that the first two laws are things that can be questioned from a very rigorous scientific point of view, but still are a great utility as far as engineering is concerned, whereas the third law is not questioned as yet on even a scientific basis. It's a very valid law that you have to look at. Now coming to Newton's second law of motion in the Principia, if you look at 1687, if you look at the original over there, of course it's written in Latin, but English translations are obviously available for many centuries now, then you would see that it's not this equal to sign that he talks about over there, but he talks about a proportionality. Okay, so in other words, he says that the force applied on a particle is proportional to its rate of change of the translational momentum, which is defined, of course, as mass times the velocity. Now, it's just a smart choice because to honor Newton as an afterthought in the later scientists named a particular unit of force as Newton. Okay, so because we named that as Newton and we defined it as the force which is required to accelerate unit mass, which is 1 kilograms by 1 meter per second squared. So if you have a 1 kilogram mass and there's just a force, which is a resultant force which is acting and which causes that 1 kilogram mass to accelerate by 1 meter per second squared, what is the force required? In different systems of unit, the F would have different values, but they chose a particular new unit for the force, which is called as Newton, to honor Isaac Newton, and therefore that is defined that way, and therefore now instead of having a proportionality sign, you have an equal to sign, which is what we mean by a smart choice of units, which implies that the proportionality constant over there becomes 1, because of which you can write this particular equation. Okay, so this is as far as the translation is concerned. As I said, the main thing which distinguishes going from the particles or a set of particles even to the rigid body is in terms of the rotation, which is what we will get on to. Okay, any of you recognize this guy? Yeah. Okay, so this is Leonhard Euler. Okay, and there's something peculiar about this particular picture. Of course, these were not photographs those days. Photographs were not common or were not done at all. If you look at his eyes, can you figure something very distinct between his right and left eye? Of course, it's a painting. It could be an error of the painter, but it was true. It was a true replica of how he looked. Yeah.
So is his right eye, like, does he have issues with just the right eye? Is that
Yeah, absolutely, yeah. So he, because we were just now talking about Sir Isaac Newton, he's British, whereas Leonhard Euler, whom we are talking about on this slide, who is the one who enabled us to move from particles to rigid bodies by bringing in the rotational aspects, and also from a set of particles based on the constraints of a rigid body to get into the actual aspects of translation. It was all the work of Euler. In fact, he did many other things which we'll look at very briefly on this slide. But Gracie is right that his right eye had issues, and he was Swiss, and he was just a century apart from Newton. So he was 1 century after Newton. So Newton, you saw his Principia was in the 1600s. This guy lived most of his life in the 1700s. In fact, all his life in the 1700s. Newton was British, whereas Euler was Swiss. He was born Swiss in Basel, and in fact, he did his education there as well. And he was a child prodigy. He completed his college when he was 15. Okay, and that left almost the rest of his life to make humongous contributions. And a lot of credit typically goes for many of these great scientists to their teachers. And in college, Leonard worked with one of the Bernoullis. As I said, the Bernoulli is a huge family of many great scientists. One of the Bernoullis was his mentor at the University of Basel, where he graduated. And he was born in 1707, and he graduated within 15 years of that. And when he was 20, he moved out of Switzerland to Russia. Those days, there was a lot of interest in science at its fundamental level, and there were some of these academies like the French Academy in Paris, the German Academy in Berlin, and similarly the Russians had an academy in St. Petersburg, which of course changed its name to Leningrad in between, and then is St. Petersburg again today. Okay, so that's the place where he went to after recognizing in his early 20s, or in fact just around when he was 20 years old, that he had an issue with his right eye. And most people in the Western Europe were not allowing him to work on cutting edge scientific projects because of that, whereas the St. Petersburg Academy was willing to welcome him, and the czars who were ruling at that point in time took care of him. And in spite of his issue with the right eye when he was 20, he was phenomenal in his productivity. In fact, how much he produced before the right eye problem and how much he produced after is much more after the right eye issue. And very interestingly, in his 50s, in between, of course, he came for a short period to a sabbatical in Berlin Academy, and then went back to St. Petersburg. And when he was around 50 years old, he lost his vision on the left eye as well. And you would expect his productivity would come down. No, it went up further. And he produced almost a paper a week. And these are high quality papers, not like today's generation where because everybody is evaluated based on the number of publications, publish all kinds of things, just incremental value additions. No, each of his papers were humongous value addition over what he had published already. And he died towards the end of the 18th century, and you would expect his productivity to go down, right? After his death? No. After his death, every year after his death, and even until today, there have been publications from Euler, there are leftover papers that he had worked on. People who came after him have been sending that out for publications. And in fact, the first few years after his death, his publication rate per year was even more than when he was alive. So that is the genius that we have over here. And he's particularly special to me because he was very special to my advisor, Dewey Hodges, who of course was bowled over by his mathematical and scientific genius, but also the fact that he had a huge spiritual inclination. And he was somebody who took as much seriousness about religion as he did about science, even in those days when these were thought to be entirely different divergent paths. Okay, so my advisor, Professor Hodges, also, I might have mentioned this earlier, used to conduct weekly Bible classes on campus at Georgia Tech, and he had a huge interest in terms of the biblical understanding, both in terms of the mythology as well as the philosophy behind that. Okay, so just to, of course, there's a lot,
So, how many publications we
atomic differences?
It's in the order of thousands. I don't know the exact number, but it's in the order of thousands, because there were certain years in which he published, as I said, one per week. So that's like 52 just in a year. So over a period of time, and he had a huge diversity or versatility in terms of the fields that he worked on: mathematics, physics, and way beyond that. I'll just list a few of that in this particular slide.
And so he had a book like Ramanujan where he had, written everything that he had, or how are his pieces even still being found?
So this is in his workspace in St. Petersburg in the academy, where he had his workspace, and he had just scribbled certain things, and people are trying to put that together. It's just like we have a genetic lineage, we have an academic lineage, and there are students of students of students, and they take interest in trying to resurrect some of those things. Yeah, Ramanujan's story is, of course, again, really fantastic. We're glad you brought that up. There could be a few similarities over there between the modus operandi. Okay, now just a few things that, because we cannot be comprehensive about Euler, it's impossible even in a full course, but some of the things especially relevant to what we are going to do. Pretty much the rest of our course here this week and next week will be focused on the so-called laws of motion, LOMs of Euler, which is, to start with, he takes off from where Newton left. That is, he looked at a particle, here looking at a set of particles, and then thinking of that set of particles to constitute a rigid body, and then looking at both its translation at the center of mass as well as the rotation about its axis. And that's where Euler made a huge contribution and is known for today, right? But that's not all. There's something called the Euler angles. I've been frequently telling you in terms of the cause and the effect. You go from the force, which is the cause, to the acceleration through Newton's first law, then the velocity, one more integration with respect to time. You get to the position vector, which is essentially the breadth of that laws of motion. So similarly, in the rotational paradigm, you have the moment, you go to the angular acceleration, the angular velocity, and then the finite rotation. That particular finite rotation is the most difficult of all these 8 things to deal with. Force is easy to deal with, velocity, acceleration, the position vector or the displacement, the moment or torque for that matter, and whether it's angular acceleration, angular velocity, these are all fairly straightforward vectors to deal with. But the finite rotation vector is very, very difficult to deal with. When you have very small rotations, you can deal with an infinitesimal rotation vector, which behaves and follows most of the rules for vectors. But when you have finite rotations, which is what most bodies have, you see the kind of rotations that an aircraft has, or especially when it's maneuvering, etc. There's a fairly large rotation that is involved, and therefore you need certain special ways of dealing with those rotations. One is called as the Rodriguez parameter, associated with another scientist, Rodriguez, but one which is very commonly used. Rodriguez is used mostly in the helicopter industry and to a large extent even in the fixed wing aircraft industry. But for aerospace engineers, when going to space, you're looking at Euler angles very frequently being used for the understanding of space dynamics, satellite dynamics, etc. So Euler angles are very, very critical over there. And of course, these slides I've already uploaded to your home, to the Teams file folder over there. And so all of these are clickable links to which you can actually go to, right? So the third thing, again, of great importance when people go to the next level of understanding dynamics from a scalar quantity. Remember that I talked to you about integrating the force with respect to the displacement to get the work done, and therefore the mass into acceleration, when you integrate with respect to space, you get something. And these two, when you're relating, you end up with what are known as functionals or functions of functions, and you have to minimize them or typically take the stationary value of that. So you have concepts like the Lagrangian or Hamiltonian, etc. And when you do that, the equations are derived by what is known as the calculus of variations, and that subject itself would not have existed but for this genius. And that is the so-called Euler-Lagrange equation, which are the governing differential equations that are there from calculus of variation, to which of course Lagrange contributed as well, which is why both these scientists are honored by this particular name, right? So, and the beauty of it is it doesn't give you only the governing differential equations, but also gives you automatically the boundary conditions and or initial conditions. So it sets up a proper initial value problem or a boundary value problem or both, which is definitely amenable to a unique solution, which is the beauty of this particular method. And you're dealing with scalars instead of vectors, so makes life much more easier for the analyst. The third thing, of course, going beyond solids to fluids, and of course, though the current standard is in terms of the Navier-Stokes to be able to understand viscous flow very well, a lot of people continue to use, where it is applicable, the Euler equations of fluid dynamics, or one of the simpler forms of it, and that's something he's known for. Again, along with another scientist, Bernoulli, he's very famous for what Nafis knows already, is the Euler-Bernoulli beam theory, which you will study in the deformable bodies as well as structural analysis course, which is the simplest theory that you can have for one-dimensional structures, like the beams that you see, which make up this building, which are able to hold such massive weight and which are bending, and those bending equations are essentially attributed, apart from Bernoulli, to Euler again. Then you also have an instability associated with structures, and typically it depends on the boundary conditions, but if it's simply supported, for example, when you increase the compressive load on a column, and you again, just like you have beams, you also have columns at the end of beams that you can see, that circular portion over there where the switchboard is. So essentially it's under compressive load, and once the compressive load goes beyond a particular value, in this case is simply supported, it's pi squared times E times I divided by L squared, where you're seeing that there's a proportionality to the stiffness of the material, there's a proportionality to the inertia, and we will be introducing a different inertia today, so I'll also clarify at that point the difference between these two inertias. One is the area moment of inertia, and what we need in dynamics is a mass moment of inertia. So these two are different, though the same symbol I is used, and L is the length of the column. So the longer columns tend to buckle much more easier, which is an obvious thing, which you can see. If you have a very long straw, for example, you try to push it down, you see that it kinks. There's an instability which develops. Okay, so again, some of those pioneering work in terms of understanding instability of columns was done by Euler, and of course extended by many other researchers who came after him. Then pure mathematics, if you're looking at, not pure mathematics, applied mathematics, if you're looking at going beyond science and engineering, you have for numerical ways of solving ordinary differential equations, there's a method called the Euler method, which is again attributed to him, where you cannot find analytically a solution. This is usually very helpful, and where you can as well, you can see that this method converges fairly quickly, and you can validate it with the exact analytical solution there. Okay, then there's something called the Euler's formula that you might be familiar with, which is essentially writing exponential of I theta to be cosine theta plus I sine theta. It's a beautiful thing. On the left hand side you have exponential function, on the right hand side you have trigonometric function. Before that, people thought that these were entirely two different kinds of things. Okay, one is essentially coming from more of an algebra kind of a thing, the other is coming more from a trigonometry or geometry kind of thing. But then he married these two, and one of the important fallouts of this is a particular value of that. So the general thing, of course, you might remember is exponential I theta is equal to cosine theta plus I times sine theta, where of course I is defined as square root of -1, right? So relating exponential to trigonometry, but a particular value of theta, if you take pi, for example, then you have exponential, and by the way, this E stands for Euler as well. So In fact, this E is named after Euler, which is why we use the letter E to denote it, right? So if you have exponential of I pi, then you know that the sine of cos pi is 0, right? It's 1, right? Cos pi is minus 1, right? Plus I sine pi is 0, right? Yeah. So I think probably for maybe I should look at pi by 2, right? So yeah, essentially if you're looking at various values, you look at pi by 2, 3 pi by 2 and 0, then you see that essentially it's relating some of the most important things like the exponent itself, which is 2.7 something, the I, which is square root of minus 1, pi, which is a very important thing, then it's the multiplicative identity 1, and also 0, which is essentially your additive identity, right? So additive identity, multiplicative identity, something which is associated with geometry, something which is associated with complex numbers, something which is essentially a universal constant. All these things are related by a very, very simple equation when you put multiples of pi by 2 over there for theta in this. So which is again correlating some of the things which people developed almost as independent bodies of knowledge. He was trying to tie them together as well. Because of the versatility of his work, he was able to get to some of those interfaces between various bodies of knowledge. This is just to name a few, but there are many others in which his work, like optics, number theory, graph theory, logic, etc. Okay, so that's as far as stories go. Now let's see the laws of motion and how he essentially applied that to a particle set instead of a single particle, which Newton had already done. Okay, so when you have a set of particles, in other words, this is a system. So Newton's second law of motion for the ith particle, if there are, let's say, n particles which you have numbered as 1 to n, so we call the generic particle as the ith particle over there, I taking on the values all the way from 1 to n. Okay, so it's a system of n particles that we are looking at. And then very easily you can see that for that particular particle, direct fallout of Newton's second law is that all the forces that are acting on that should be equal to the mass into acceleration of that. Okay. Now some of you might be familiar with so-called Einstein's summation convention, where if an index is repeated, there is an implied summation over that. Okay. But remember that Newton's work and even Euler's work were much before Einstein, and therefore we didn't have that system of that convention at that point. So for our course in dynamics AE2220, when we write the index repeating, it doesn't mean there is a implied summation. So in other words, right hand side is just one particular value of I for both the mass as well as the acceleration. So those of you are already familiar with that Einstein's summation convention, implied summation convention, please don't apply that to some of the equations that we will write on the slides over here. This is more taking from the way in which Euler developed over Newton, so taking the similar kind of an approach over there. Okay, now so this is an equation just for the ith particle. Similarly, there will be n minus 1 more equations for the remaining particles as well. So what it's saying is that all the external forces that are acting on it, which is essentially the resultant of that, is what we denote by F subscript I. Okay, so this is coming from things which are external to the system, not external to the particle, but external to the system. Now within the system, there are not just one particle, but multiple particles, right? So those particles are obviously interacting with each other. So there are interactive forces between the particles as well, which we will call as Fij. Okay, so the beauty of the universal law that we talked about is that Fij equal to Fji. So in other words, what force I is exerting on J will exert on I. So what is included over here is all the forces exerted by J, because this summation is over J alone. Okay, this equation is for a fixed I, and the summation is over J, even though it's not written over here. J is equal to 1 to n is the summation. And so all the other particles, whatever forces they are exerting on the ith particle is what is contained here. This of course will not go to 0. But if I have a double summation on this, I sum over both I and j, then it has to go to 0, because the Fij and Fji will cancel each other out. Okay, but here, since we are looking at just one particle and what the other particles are doing to it, so you will have a contribution from the other particles even though they are part of the same system. So that's as far as the left hand side is concerned, the total forces, some coming from outside the system, some coming from within the system, and everything put together in an algebraic sum, typical vector sum that you have. So this is pretty much applying Newton's second law. So you have force on the one side, total force, and on the right hand side you have the mass and acceleration of the particle on which this is acting. That particular particle has a mass mi and it has an acceleration ai, and therefore this is what this is equal to. This is quite straightforward. But what Euler did with this in terms of taking it forward is what is quite interesting, by invoking not only Newton's second law but Newton's third law as well. So what he did is, of course, directly he went ahead and summed this up not only over j, you already had the summation over j, but now you sum over I as well. Okay, so when you sum over I as well, as I said, the double summation of Fij goes to 0 because of Newton's third law, the law of reciprocity, right? So the second term on the left hand side drops off. The first term, of course, becomes a summation over I equal to 1 to n of Fi, which is the total set of forces that are acting on all the particles of the system, or you can say the total forces acting on the system, right? So because all the particles constitute the system, and therefore when you say all the forces acting on the particles of the system, it essentially means all the forces acting on the system itself, right? So that's your left hand side. Now coming to the right hand side, as of now we don't know how to simplify it further, but there's a huge simplification already, because instead of dealing with n plus or n minus 1 plus 1, which is a total of n forces that you had on the left hand side, now you're dealing with just one particular sum on the whole system that you're dealing with, which is much simpler to deal with. So already by summing over all the particles, we have arrived at some simplicity for the left hand side, but the right hand side remains complex in terms of summing over the masses and acceleration products of each and every particle. Oh, again, both the summations here of course are from I equal to 1 to n. So it's different from this summation, which on the first equation was from j equal to 1 to n, whereas these two summations in the second equation are over I equal to 1 to n. Okay, now of course I already mentioned to you the reason why the second term on the left hand side drops off, because the interaction forces are equal and opposite due to Newton's third law of motion, as explained in Newton's not due to, but as explained in Newton's third law of motion, and therefore do not contribute to the overall system dynamics. It contributes to particle dynamics. Those individual particles still suffer from the interactions between those particles, but when you're looking at it from a overall system point of view, then there's not that much suffering. Again, this has some bearings in terms of life for us. We're looking at all of us as individuals, we'll also look at all of us as a team. Then the interactive forces, when you're summing it up as a team, do not have much of a bearing on us. If you're always thinking of ourselves as only as individuals, tiny puny individuals, then certain things bother us which need not bother us when we are looking at ourselves as just a part of an overall system, because you see that all of those things which were troublesome in nature have vanished, and it's only the external forces that you have to do. And as you keep increasing the size of the system, then you see as it tends to infinity, essentially becoming all inclusive, and essentially there's nothing other than outside you. You're essentially making your left hand side equal to 0. You're ending up with Newton's first law, where there's no force acting on the system, then it remains in a state of steady motion. That's lessons for life from the dynamics of particles and systems of particles as well. Okay. So next, let's check out, as I said, we have simplified the left hand side. Now we want to simplify the right hand side as well, which is what we will do. Okay. So now here's where we need to introduce this concept of the center of mass. Instead of dealing with each and every one of those n particles and summing over their products of their masses and accelerations, can we deal with just one point? That is the whole idea over here, right? Now the particles' acceleration is of course related to their position vectors. Remember we talked about the cause to the effect, and the effect we talked about the position vector. We take first derivative with respect to time. In the inertial frame we get the velocity, then we get the second derivative, we get the acceleration, right? So we know that the acceleration is therefore related to the position vector through time derivatives, which is what this simple thing says for the system of particles, because what we had on the right hand side in the previous slide, right, even at the end, was the summation of mi ai. Now I can write that ai from the kinematics that we have already studied in the beginning of this course as d squared by dt squared of the position vector. So now this position vector ri very clearly is from a point which is fixed in the inertial frame of reference, which you can call as O, to that particular particle which is pi. Okay, so that position vector we are calling it as ri, and the default value of the inertial frame is the inertial frame of reference with respect to which both these derivatives, the second derivative, is essentially taken, right? Then mi remains as it is. Now we know that this is actually an approximation, mi ai. The reality is that it's the rate of change of the translational momentum. So we can as well put both inside and take mi inside as well. So which is essentially d squared by dt squared of mi ri. Irrespective of whether mi remains a constant or not, this is the actual valid thing, equation that we have, right? Now this summation and the second derivative with respect to time can be interchanged. You can either take the derivative first and then take the summation, or you can take the summation first and then take the derivative. And this is something that we already learned as the basic rules from scalars. We were extending it to vectors using commutativity, etc. And we slowly, gradually developed that. Same thing we are now applying to a specific derivation over here, where we are interchanging d squared by dt squared, bringing that up front and taking the summation inside into the bracket, which is what we have over here. Now we get into something very, very interesting, that we have a summation of the mass times the position vector. Now the summation of mass times the position vector in general will be non-zero, but there will be a specific point for which it will become zero, and that by definition is the center of mass. So center of mass is defined as that particular thing for which this total summation essentially goes to zero, because essentially they're balancing it out. So you just think of two particles of the same mass which are there, then you can see that any arbitrary point if I take, that will have a non-zero value. But if I take the point which is the midpoint of the line joining these two particles, you can see that these two are going to cancel each other out, because the masses are the same and the position vector is essentially the negative of one is the negative of the other, and therefore they will cancel each other out. So that's the direction in which we are moving. So here of course we are assuming constant particle masses for which this is valid, but it's not necessary for the right end that you're talking about, right? Now therefore you define this center of mass location as the ROC, where O is the point fixed in the inertial frame of reference I that you introduced in order to handle this motion and also all the time derivatives. And C is the new point that we are defining now, is the center of mass. So the position vector going from an inertially fixed point to the center of mass of any system of particles that we have, where there are n particles, each could be of different masses. The simple example that I talked about, we said m is equal, but it's not necessary. That I just wanted to get you to intuitively feel what we are getting into. But when you have that, when O is any arbitrary point, then you see that it is just a weighted average of the masses, which is why this is called as a center of mass. On the other hand, instead of masses, if I had weights, like Daniel and I were discussing in the beginning of the class, instead of masses, if we had weights, which is mass times the gravity, right? And if gravity was not the same at each particle that is there, because the particles, now you can think of the system as the solar system. Okay, the system of particles could be the solar system, where you have all the sun and the Mercury, Venus, Earth, Jupiter, Saturn, all these things, bodies, even those which are probably not considered planets anymore, like Pluto. All of these, if you think of as particles, then you essentially see that you can do something like this, and the G will vary for that. Okay, G at each one of these locations at the center of the Earth, for example, very different from what it is at the center of Mercury or center of Pluto, right? So then you could see that the center of mass and the center of gravity will be different. What we need from this point of view as of now is just the center of mass. Okay. On the other hand, if you had areas, it would get you a 2D centroid. If you had volumes instead of masses, you would get a volume centroid. Okay, so that's essentially volume centroid, area centroid, mass, center of mass and center of gravity. They all have a very, very similar definition, just that the weighting function is different from for each of them. And this M, of course, is the total mass of the system, which is defined over here as the summation over all the MIs that you take. Now we can go back and check what we were saying over there, that this goes to 0 if it's the center of mass. Is it true? So if this goes to 0, then you see that ROC is 0, which means that O and C are coincident. In other words, the point that we chose, luckily we chose a particular point which happens to be the center of mass of the system, and therefore ROC equal to 0. So that's a special case, but this is when you do not know the center of mass of a particular system of particles, because they're all at different locations, arbitrary locations, and they're all of different masses. So you have to actually calculate the center of mass. Then you choose any arbitrary point O, as long as it is fixed to an inertial frame of reference. That's good enough for us. It could be any point. There are infinite such points. You can choose any one of them, and then you try to get to C by using this particular equation, right? Now if you shift O to that C, then this whole thing will become 0, and that you can start using that as O if, of course, it's a part of the inertial fixed frame. It may not be, because the body might be accelerating, in which case O will not be no longer be inertially fixed, and therefore you cannot use that, right? So I guess this is quite clear, because essentially it's a concept that you knew, but from middle school level, but trying to introduce it from a vector point of view, and also trying to introduce it from a more generic point of view, and trying to elaborate on the analogies between centroid, center of mass, and center of gravity, so that you see all of these are coming under the same paradigm, and you really don't need to break your head into learning each of them separately. Essentially, you're achieving the same purpose, just that the weighting function is going to be different for each one of them. Okay, so therefore, once you take the mass to the left-hand side on this, you see that summation MIRI can therefore be written as mass times the position vector from the inertially fixed point to the center of mass of that system of particles. So wherever this summation comes, this was the troublesome thing that we had in the previous slide. I can replace it by just this product. I just have two quantities to deal with. One is the total mass of the system, all the particles masses put together. The other is just the position vector from O to C, and therefore I don't need to deal with that many n number of position vectors, n number of masses, etc. Just one single mass of the entire system and one single position vector of the center of mass of that system. Okay, so now this is what we're going to do. We're going to substitute this over there in that particular equation. So instead of what is there within the bracket over there, I can just put m times ROC, which will make things very simple. Again, if m is a constant, m will come out of that, and you will just have d squared ROC by dt squared in an inertial frame of reference. And you know that the first derivative of r in an inertial frame will give you velocity, second derivative will give you acceleration, but of which particle? It's essentially the particle that you're looking at from O, which is essentially the center of mass, which is not actually a particle, but essentially we're saying that if we were to lump all of those particles which had distinct identities into a single location, which is the center of mass of that system, then you see that it is that, and therefore d squared ROC by dt squared is nothing but the acceleration of the center of mass, which is what we will utilize. So already we had simplified the left hand side of that equation. Now we have a simplicity for the right hand side. We will combine both of these together. Okay, and what we end up with is, of course, what is known as Euler's first law of motion. So this is the beauty of how science develops, there is somebody before us who has done some pioneering work. We take that as a starting point and then try to add value to it, which is what Euler did from Newton. So Newton already had for a single particle. Now Euler is extending that to a system of particles and saying that the sum of the forces which are acting on all the particles of the system, which means that it's the total force acting on the system, in other words, is equal to the mass of the system, not of individual particles, but the mass of the system times the acceleration of the center of mass of that particular system. Again, all of these are with respect to the inertial frame of reference, the chosen inertial frame of reference. Okay, that's the default because we don't have other frames we're talking about right now. Now, so how do we get there? Obviously, we're just going to combine the information that we had from the previous two slides. So you're looking at the right hand side, which is essentially what we had is a d squared by dt squared of a sum of the products of masses and the position vectors. Those position vectors Ri, once again I need to stress, is from O to an individual particle, O to that whatever mi, whatever had the mass mi, right? So now in the end of previous slide, we saw that that summation can be replaced by just a product of two quantities of the system rather than of individual particles, which is the system mass times the position of the center of mass of the system. And once we do that, if m happens to be constant, I can take that out, and then I have that d squared by dt squared is with respect to an inertial frame I, and therefore because it's of a position vector of a point with respect to an inertially fixed point, therefore it becomes the acceleration of that point, and therefore it is A of c. Okay, so now the center of mass definition implies that the if you're looking at the sum of the so essentially what this bracketed term replacement is telling in words, if you look at, essentially you're saying that the sum of the product of masses and accelerations of individual entities which make up a particular system is essentially total mass times the center of mass's acceleration. Now, though most of these things we are doing for particles, eventually we will see that you can think of a big body which is made out of sub-bodies. So essentially, for example, a sphere, and you can think of a robo. So a humanoid kind of a robo, you can think of a sphere, you can think of a cylinder, and two cylinders essentially are made of each of this, those, you know the velocities of their mass centers, and you know the masses of each one of them. Then you can do the dynamics of the entire robo, right? So that's something like that. So right now we are talking of particles, but we can move it soon to sub-rigid bodies. So a bigger rigid body, a complicated shaped rigid body made out of simply shaped rigid bodies of spheres and cylinders and cones, etc., for which we might have the information already. Typically, most dynamics textbooks, including the book that you are referring to, have as an appendix typical for standard kind of shapes, both 2D as well as 3D. They will give you the center of mass location, etc. Of course, we will introduce another concept shortly, maybe in the afternoon class. We'll talk about the second moment of inertia, which is the mass. Okay, just like this is the center of mass, that's the second mass moment of inertia. And when we do that, those things will also be given for such standard shaped bodies or cross sections, 3D and 2D respectively. And you can just take that and construct for a more complicated shape which is made out of those simpler shapes. Okay, so the sum of the particles mass and acceleration products of the individual entities is equal to the total mass of the system times the center of mass's acceleration, is what that thing says in words, what we found in the previous slide. And the same thing, very interestingly, is also true for, it might seem silly, but it's a very powerful thing that we're talking about now, is valid for the transcendental, with apologies to Transcendental Meditation and Trademark, which also use the same symbol Tm. This, we're talking of the translational momentum, okay? So Tm, so whatever we have said for the center of mass is now valid for this. In other words, the sum of all the particles' translational momenta, momenta being the plural of momentum, so the sum of all the particles' translational momentum is equal to the translational momentum which is based on the total mass and the center of mass's velocity. So This is another way of saying the same thing. Here we are putting in terms of mass times acceleration, but mass times velocity also you can see, and using the same logic that we did in the previous slide, you can easily show that mass times velocity also follows that. Instead of the second derivative of with respect to time, we are just using a first derivative with respect to time of the position vector. So therefore you can see that if you want to get to the momentum of the system, you don't need to sum that for each and every individual particle. You can take the total mass of the system as a whole and its center of mass is velocity, and then you take the product of that. You're already having the overall system's translational momentum. Okay, so that's what we call as, what we have at the end of this slide is what is called as Euler's first law. Just like you had Newton's first law, second law, third law, we are going to get into Euler's first law, which we already did in this slide. We are going to get into Euler's second law as well, and that's essentially talking about rotation, whereas this one, first law, talks about translation of the particle set. Yet we have not yet reached the rigid body or rotations. We are only talking of a set of particles, but that is good enough for us to get into rigid bodies shortly, because you can treat a rigid body as a set of particles. Okay, so for translation we have the governing equation of motion, and which is you should remember is called as the Euler's first law. Okay, now let's extend this to rigid bodies. So what we did so far is to look at a system of particles. Okay, now we want to extend the same thing what we did at the end of last slide to rigid bodies, by considering that as to be nothing but a system of particles. And if you look at the end result of this slide and the previous slide, what do I have here on the left hand side? Summation Fy, and on the right hand side MAC. If I go to the next slide, I see I have exactly same thing. So it's absolutely no difference whether I consider it to be a system of particles for which this was valid, or for a rigid body for which this is valid. And right now it seems obvious, but at that point in time, when people were looking at rigid bodies as entirely different kinds of entities compared to a system of particles, it was a major breakthrough to see that the same thing which is valid for a system of particles is valid for a rigid body as well. So you have exact same equation, exact same variables over there. Okay, let's see how this goes. So you have to, of course, replace the summations on the right hand side with integrations, because now you're dealing with continuity. You're not dealing with discrete particle set where summation could do. So instead of summations, you're going to have integrations, because right adjacent to each particle you have one more particle, and so on and so forth, making up a continuum. So that for that continuum, when you want to do a summation, the equivalent is an integration. Okay, a volume integration for 3D, or a area integration for 2D. Okay, so the center of mass location, therefore remember that the one we had for particles was just a summation of the products of the position vector and each individual particle's mass divided by the total mass. Now instead of individual particle mass, we are looking at an infinitesimal mass element dm. Okay, you can think of around that particle, essentially it's having a finite volume. Now a particle is a point which has zero size, but now we are moving into a finite size, still infinitesimal, and therefore we are calling it as dm, right? So that differential of mass is what you're looking at, so that you can get to continuity. You're replacing the summations with integrations in the limit, and then of course the position vector is not to a particle but to the center of that infinitesimal mass dm that you have introduced. Okay, so you can think of it as an infinite arrangement of those particles instead of the finite set that we had over there, and around each of those particles you're essentially coming up with a finite volume, and you're essentially treating that as that mass dm that you're talking about over there, and therefore the same similar kind of an equation holds good. Okay, so now we introduce also the density, because one of you also referred to different densities when you have different materials, and when you do have the same material, or you have the same density, and therefore certain things might remain the same. Okay, so that's what we want to get to here, because we're entering into continua. So therefore instead of an integration over mass, which is very difficult to do, you want to do a volume integration. So to do a volume integration, you can replace the infinitesimal mass element dm by an infinitesimal volume element dv multiplied by, of course, the mass density. Okay, this word density is again used in various parts of engineering by different meanings. You could have, for example, the crack density, how number of cracks per unit to volume, etc. So unless and until specified, the default is the mass density. But when you are dealing with multiple densities, it's always good to specify it clearly that this is the mass density that we are talking about. In other words, mass per unit volume, not something else per unit volume. Okay. So then coming to ROC, therefore, now all that you're doing is to replace that dm with this rho dv in this numerator in the integral integrand, and therefore that's what you have, rho r dv divided by m, which of course is nothing but the integration of dm. And again, dm you can use the same thing, rho dv, to see that the total mass is, of course, the integration of the density times dv. So when you have different materials making it up, or the same material in different phases that it might be, etc., then you have your rho changing across. But of course, you can't typically apply this for other than solids, for fluids, be it liquid or gas, because it's no longer a rigid body. Okay, even solids, in fact, in truth are not rigid bodies. It's a stretch of an imagination if you want to do that for liquids or gases. So here we are talking about mass is equal to an integration of rho dv. So it's only that the definitions have changed. Your mass definition has changed, your ROC definition has changed. Changed in the sense that you are replacing, in both cases, what you had were summations, now you have integrations. In both those cases you had MIs, now you have rho dv's. So that's all that you have changed. Okay, but the definition, but the end result, because this is how now you're defining your ROC and your M, therefore your final equation remains the same. It's the same ROC's second derivative with respect to an inertial frame of reference, with respect to time, of course, and that's your acceleration of c, the center of mass of the rigid body instead of a system of particles, and that's the mass of the rigid body, and that's the sum of the forces which are acting, the net force which is acting on the body. Okay, so this is precisely what I said just now. This is sum of forces that you have, can be thought of, therefore your right hand side has become fairly simple. It's your acceleration times dm, because it's your second derivative of the position vector, and once you have that, you see that you can again replace dm, the infinitesimal mass, by rho times dv, which is your in terms of your infinitesimal volume element, and therefore this is what you have as Euler's first law of translation for rigid bodies. So we are not done with the kinetics of rigid bodies, because we are taking only 3 of the degrees of freedom that a rigid body can generally have, which are the 3 translations in the x, y, and z directions. Essentially, by tracking the center of mass, how it is moving in these 3 directions, we are able to do that. Okay, and it's exactly same as what we had or earlier, as I said, for the set of particles, right? So now this is your equation that you have as Euler's first law of motion. Any questions or doubts so far? I think it's fairly straightforward, right? Next, let's get into a little level of complication, and this is something that I introduced orally just a few minutes back, where we said that typical rigid bodies may not be just a hunky-dory sphere or a cone, etc. It might be a fairly complex shape, but you can always think of it in a modular fashion and reconstruct it with made out of multiple parts, each of which might be a simpler geometry, and therefore can we utilize that to our advantage in making some of those calculations in terms of the variables that we introduce, like the position vector of the center of mass, the total mass of the system, etc. Yes, we can. So that's what we will see in this slide. The standard rigid body shapes that we have, most engineering books, as I said, dynamics books, as I already said, will list the values of center of mass. For example, for a hollow sphere or a solid sphere, it will be at the center of the sphere, etc. So these kinds of things. A little more involved will be a cone or a pyramid, for which the height of the center of mass you may not be able to guess purely from symmetry. Then you will have, of course, you can calculate it using those integrations that we had in the previous slide, but those were things that you're done and dusted with in middle school or high school. You don't need to keep redoing them. You might as well take it from the tables and start utilizing that, so that you can get on to the next level of value addition to the knowledge, which is what you would do over here, right? So center of mass locations are given in books for standard shapes, but if you have some shapes like which are axisymmetric bodies like a cylinder or a cone, you know that on the axis of symmetry is where the center of mass will lie. It's only the other coordinate or one or two coordinates that you have to determine. For example, for a cone, you know that there's an axis of the cone and the center of mass has to be on the axis of the cone. But at what height? What height from the base or what depth from the tip of the cone is the actual center of mass? That's not something which is intuitive. You have to actually calculate in order to get to that, okay? So it will depend on the geometry of the specific cone that you're dealing with, right? So for those kinds of things, again, you will have the values in the tables and you can just take that. So that's as far as axisymmetric bodies are concerned. Another which is of great significance for us in the aircraft is that you know that when an aircraft, a fixed wing aircraft that you have, you see that the plane which is passing through the nose and which is perpendicular to the span of the fixed wing, that is a plane of symmetry. So in other words, the port and the starboard are for most phases of flight symmetric. Some examples you can think of where there could be an asymmetry between the port and the starboard in a fixed wing aircraft. Yeah. So loading, also it depends on, let's say, in a military aircraft, for example, you have set forth one weapon on the one half of the wing. The symmetric counterpart is still there, right? So for a few seconds at least, until you use that, there is an imbalance that you have. And so many times this will, of course, be controlled using some of your rudder and roll, the aileron controls, etc. But for most parts, for most phases of flight and for most aircraft, you will see that the plane which is perpendicular to the span and passing through the nose of the aircraft is essentially a plane of symmetry, and therefore your center of mass will be on that plane of symmetry. Just like for bodies of rotation, solids evolved by a revolution, you saw that the center of mass is on the axis of rotation. Now you see when you have a plane of symmetry, one or more, you will see that it will be on the plane of symmetry. If it's two planes of symmetry, like for example a cuboid has two planes of symmetry or three planes of symmetry, then you know the intersection of all those three is a point, and therefore it will be at that particular point, okay? So we can take advantage of that as well, okay? So many situations, but typically most of those will already be in your book, so you can either take it from the tables or intuitively you can take this, especially when you have more complicated shapes, and those complicated shapes may not actually be presented in the tables, but you can probably recognize this aircraft is a complicated shape. You will not have for the aircraft being listed in the table, obviously, right? So, but you know that there is a plane of symmetry, and therefore I don't need to calculate the y coordinate which is along the span of the center of mass. I need to only calculate the x and z components or measure numbers of the center of mass. So that's what you take advantage of, right? Similarly, for a rocket, you might see that you could think of it as an axisymmetric kind of a body for first cut analysis, even though it might have solid rocket boosters, etc. And therefore, you know that the axis of the rocket is where the center of mass will be, but at what height you don't know. So that you have to calculate depending on the stages and their contents, right? So many rigid bodies, as I said, are a combination of standard shapes that you would have, and therefore you can use the particle formula, as I said, because instead of particles you now have sub-rigid bodies, okay? So in other words, shapes which are standard shapes making a complicated shape. So you can use the particle formula. So in other words, each of those standard shapes, you concentrate their masses at their own centers of mass, and then you have to arrive at the center of mass of the system as a whole using those centers of masses and the masses, which is like dealing with a system of particles, okay? So use the particle formula, and you'll have some examples of that in the upcoming homework, which you'll present shortly, right? So they use particle formula to calculate the rigid body's center of mass using each of those individual parts masses, mi's, I equal to 1 to n, where n number of subparts are there for the overall body, and of course the center of masses position vectors. So each of them has their own position vectors. So you will introduce a particular frame of reference and origin for that O. From that O, you will know the position vectors for each one of those centers of masses of each one of those parts of the rigid body and each of their masses. And so treating them all as concentrated masses at those locations, you can arrive at using the particle formula that we already presented at the beginning of today's lecture for calculating the overall center of mass. So this is what essentially those formula were that we had for the particles, and it is valid for the subparts of the overall rigid body, which is I want to get from an inertially fixed point O to the center of mass of the complicatedly shaped system or rigid body. And to do that, all that I have to do is to break it up modularly into simpler shapes. For each one of those shapes, I want to calculate the location of the center of mass of that part from the same point O. From the same point O, I want to calculate the position vector, and then I have to multiply by the mass of that subpart, and then I sum them all up and divide by the total mass of the rigid body, which is the sum of all the parts masses. And then I have that in the denominator, so then I can get to a vector which gives you the location of center of mass of the system, or rigid body rather, now from the origin O, which is fixed to the inertial frame. Okay, now translational momentum, we already introduced this, but a little more formally and in terms of utilizing that in the equation of motion. We already have Euler's first law, which helped us to look at the translation of both systems of particles as well as rigid bodies. Now we want to see, can we put it in terms of some other quantities, make it look even simpler? And yes, we can, if we can do it in terms of the so-called translational momentum. And that translational momentum in this in some books is, and also in our slides, we will use L, but typically in a lot of advanced dynamics books, L without the vector is used for Lagrangian, and therefore they use P, uppercase P, to refer to translational momentum. Okay, so just be aware of that. So either P or L can be used, but L, if it's a vector, then it's a translational momentum you're talking of. L without a vector is a Lagrangian that we'll be dealing with, which is a combination of the kinetic energy and the potential energy with appropriate algebraic signs. So leaving that aside, right now our focus is on the translational momentum, and that is L. And so we are essentially saying that the total force that is acting on the rigid body is equal to nothing but the time rate of change of the translational momentum. And that's quite straightforward, but we can just look at how this is arrived at. It's quite obvious from whatever we have done so far, but I'll take you through the steps. So for the individual particles, we have introduced for the ith particle, its translational momentum is equal to its mass mi times its velocity vi with respect to an inertial frame, right? Now this is true for a particle. Now we have a system of particles, and then we treated rigid body as a system of particles as well, which is what we will walk through to get to this last equation that we have on the slide. So the set of particles that you have, therefore you're just going to sum up over the equation on the first line. So that is for just for the ith particle alone, what is its translational momentum. This is for the entire system of particles. You have to sum over each of those I, which of course Einstein would say that's obvious, it was already there, a sum over there, but this is pre-Einstein, and therefore there's no implied summation convention over there. So you have to explicitly put a summation there and say I equal to 1 to n for a discrete set of particle system. Okay, so in terms of the particle set, center of mass, we want to get that. So therefore we can write this particular equation mivi, keeping mi the same. We want to write the velocity from its first principles as the time derivative in an inertial frame of the position vector ri, which is from O to that particular particle. So whenever you use uppercase ri, remember that it is from O, which is an inertially fixed point, to that specific particle pi that we are tracking, and therefore that is your Ri that we are doing, and the default, of course, the pre-superscript is I for the time derivative. Okay. So then the more general case is where the mass can also vary, and therefore it's taken inside, and therefore you have mi Ri as a summation, and that's the d by dt of that, again with respect to an inertial frame of reference. And now we know that this summation is what we introduced for the definition of the center of mass, which is what we put over here. Is the, instead of the individual particles masses, it's the total mass of the system of particles, and it now, instead of the individual particles position vectors, you now have the single position vector, which is the position vector from O to the center of mass of the entire system, not of individual particles, right? So when you have that, and again in a special case where m is a constant, comes out, and dr by dt in an inertial frame of reference is nothing but vc, because it's going from an inertially fixed point to the point whose velocity we are writing over here, vc, right? So next, for the rigid body, of course, the only difference is instead of summations, you'll have integrations, and where you had mi, you will have dm, which you will replace as rho dv. Okay. So the same thing that we did for an earlier derivation, we are doing over here, and we introduce this the translational momentum L, and once we do that, we can resubstitute back into our equation, and then we see that the summation of the forces, all the forces, external forces. Remember, we already got rid of the internal forces, one particle acting on the other within the system, that's already gone because of a double summation. Now we have a single summation over all the forces acting on all those particles, and that is equal to the rate of change of the translational momentum, time rate of change of the translational momentum with respect to an inertial frame of reference. Okay. So now what we have done so far is just to get into kinetics by looking at purely translations, and since we already had a very good understanding of the translation of a single particle, we graduated it to a system of particles, and then we thought of rigid body as a special case of a system of particles, and then we applied that there, and we have expressed the same Euler's first law in many different ways. One is essentially in terms of the velocities, the other is in terms of the translational momentum. Depending upon a specific problem, one might be more convenient to utilize compared to the other. Any questions so far? Okay. Now, maybe I'll, because it's a new topic, I'll probably take it up in the afternoon. So now that we are done with translations, where we introduce the concept of translational momentum, which we denoted by L, now we will introduce a concept called the angular momentum, AM, which we will denote with H, uppercase H as the vector, and instead of translation, we're going to deal with rotation. So with this, that and this put together, translation and rotation, the entire motion of the rigid body, all its 6 degrees of freedom will be taken care of, 3 through translation and 3 through rotation, which we'll be dealing with in the afternoon. But this is of course for 3D motion. When you're looking at 2D motion, things become much simpler. For example, the aircraft moving in its plane of symmetry is essentially the altitude changes, the forward velocity, and therefore the distance, and of course the pitch that it has. So that these are all happening in the plane of symmetry. So things become much more simpler. You have 3 degrees of freedom, 2 translation and 1 rotation. And whenever you have only one of a quantity, you can deal with scalar equations. Like you are dealing with a lot of the problems I saw, you're dealing with omega almost, it's like it's a scalar quantity. Kind of luxury that you have, or convenience that you have, is purely because that was the only omega that was there, and you could deal with that, and it's always about k hat, and therefore you're generally dropping off the k hat. Like in some cases we are dropping off the I as the inertial frame of reference with respect to which we are taking d by dt. Okay, but it's always good to remember that at your back of your mind, and especially when you're doing derivation or talking to somebody, to mention that at least orally, if not in writing, so that you're aware that when you go to more complex problems, which is the run-of-the-mill kind of problems you eventually will solve, then you will have many frames of reference you will have many degrees of freedom, many rigid bodies making up, or in fact eventually go into flexible bodies. Then all of these things, being more precise in terms of the frames of reference, etc., will come in really handy. And each of the topics, when I'm introducing, I'm also mentioning a particular section. For those of you who are interested in going looking at the book, I don't recommend that necessarily, but in case you just want to know a little more about it, you are welcome to. So I'm just correlating that. It's not kind of, the content here is not directly taken from the book, but more or less the same kind of notations of variables might be used, and where it is not, I will be mentioning specifically so that you can see the same thing, whether it's in the book or in the slides. So let's meet at 2 o'clock. Thank you.